Hi everyone, this is the second example of chapter 4. It is question 49. Let's read the question. Question 49. Two electrons, initially at rest in space, are separated by a distance of 10 centimeters. Calculate the velocity of both electrons when they are A, 20 centimeters apart, B, a vast distance apart, and part C, in this situation, both electrons will always have the same speed. Explain why. So first, let's draw a diagram. We have two electrons. Now, by the way, both electrons will share the same mass and charge, so that's an important distinction. They are initially at rest and separated by a distance of 10 centimeters or 0.1 meter. We release them, they start accelerating, and we want to find out what is the velocity, let's call it V1 and V2, when they are a distance of 0.2 meter apart. All right, so the first thing, we need to calculate the difference in potential energy from when they are 0.1 meter apart to 0.2 meter apart. We use the difference in potential energy, which is equal to the Coulomb constant multiplied by the charge. Note, they both share the same charge. It is E squared in this case, all right? Well, each of them has a charge of E, but since we have two of them, we multiply, it becomes E squared. We open the parentheses, 1 divided by the final position, minus 1 divided by the initial position, and we get a change in potential energy of minus 1.152 multiplied by 10 to the power minus 27 joule. All right? That's our change in potential energy. We know that minus delta, the change in electric potential energy, has to equal the change in kinetic energy. Now, there's a catch in this question. And the catch is we have two objects which each of them has separate kinetic energy. All right? So the total change in kinetic energy is 1/2 the first mass, which is the mass of the electron. Open the parentheses, the final velocity square minus the initial velocity square, and the same thing for the second electron here. Now, at this point, we have two unknown, one equation. We need a second equation. And this second equation is the fact that both electrons need to have at all time the same velocity. Why? Because of Newton's third law. For every action, there's an equal and opposite reaction. So let's say this is our first electron and there's a force from the second electron acting on it. Because of Newton's third law, there's an opposite and equal reaction. So both of them will have the same force on them. Well, force is equal to MA. They both share the exact same mass. Because they both share the exact same mass, because both force on them are equal at all time, that means they have to have the exact same velocity at all times since they started at the exact same velocity. Now that we know that they share the same velocity, we combine both of these values and basically the mass are the same, the velocity are the same, so we simply add that term to that term and we remove the 1/2. We end up to the electric potential energy is equal to the mass of the electron. By the way, the mass of the electron is 9.11 multiplied by 10 to the power minus 31. The initial velocity is 0. We got our V and its final velocity here. So we isolate our final velocity and we get 35.56 meter per second. All right, so that's it for part A. If you need to write any of this down, pause the video. I'm gonna erase at least this section over here to solve part B, all right? Oh, that's over here. All right, so in part B, and I'm gonna remove the A over here, we use the same exact logic. So the change in potential energy, it's just that the final position is different. It's not 20 centimeters, it is at a vast distance, which we can approximate by using infinity. Now note, 1 divided by infinity is 0. Once we input these values, we get minus 2.3 multiplied by 10 to the power minus 27 joule. All right? Now we want to find the final velocity. We use the same principle. We equate the potential energy to the change in kinetic energy. And I'm gonna save a step here. We know that both velocity has to be the same, and we know that the initial velocity is 0, so we end up, as in the part A, with this step over here. And we got the final velocity, once we isolate it, of 50.3 meter per second. So that's the answer to part B. All right, let's read part C. In this situation, both electrons will always have the same speed. Well, we answered that question. They have the same mass, they have the same charge, they start at the same speed, and both force, because of Newton's third law, both force is equal at all time. All right, so that's it for question 49. Let's move on to another video to solve another example.